Hello everyone, I hope you all are doing great. We heartily welcome you all to our YouTube channel CAD CA Master. If you enjoy what you see, hit the subscribe button and turn on the notifications so you never miss an upload. Well, in the previous session we had seen few basics of FEA and FEM CA related things, and today also we'll be taking you through few of the basics which is very essential for the beginners. You could see the agenda. We'll be starting with the effect of stress, and we'll see the true stress strain and the engineering stress strain curves and how they are impacting and how we need to utilize them. Young's modulus, Poisson's ratio, so assumptions in FEA related to geometry, material and boundary we'll see, and then we'll also see how the assumptions are taken into account for the fasteners as well. Okay, for the static analysis I mean, yeah, and even for the some of the linear and non-linear dynamic analysis, and it is not considered for everything, but here we are mainly focusing on the static analysis, and it might also be carried forwarded for the non-linear and dynamic analysis as well, but in few cases only. Well, the first question here is using different material will give you a different stress for a given strain. So let's say we have the steel, aluminum and copper, different materials we have it. So will they give a different stress or will give a single stress for a given strain? In short, if we have a material, like each material will give the different stress results or it will give the same stress results. I hope the question is clear, right? So this is the very basic question which everyone needs to understand and everyone needs to know how this is impacting. Okay, I would like to take you through the complete details. Please do concentrate because it's quite important. Okay, so now if you calculate the stress by using the Hooke's law, that is stress by strain equal to Young's modulus equal to stress by strain when it is stress Young's modulus into strain. So here the Young's modulus will change, right, depending upon the material. Just remember that. Yeah, each and every material will have the different Young's modulus. Yeah. Okay, then the relation between the stress strain will be constant for a given strain. Let's say if the strain remains constant, stress equal to strain, right? In short, this is what he wants to tell in this statement. Now, this is the reason why when you have a column under the axial force will be always derive the same stress which is equal to force per unit area. So if we have a pure axial force on a particular column, so we'll give the what the same stress, we can say constant stress. So here when it comes to stress, we have the force per unit area, right? So whatever the force you are applying divided by area. So if the cross sectional area remains the same, if you are applying the force, then the stress should remain the same. Okay, now just remember the statement. The strain will change if you change the Young's modulus, correct? So if the Young's modulus is less, and ultimately displacement will be more, and depending upon that the strain will be more, right? But the stress will remain constant for the same axial force and the constant area. This is what I wanted to convey. So if you have the force for unit area, if you have the cross-sectional area like this, let's consider this image itself. Let's say this is a kind of structure. It is made of steel, copper, and we can consider another material, aluminum, let's say bronze, even consider whatever the material. So area remains the same for each and every material, right? And then stress which is equal to force applied per unit area, and then stress should remain same, right? So if you account material for non-linearities, the Hooke's law will not be applicable, that we everyone knows, right? So let's say Hooke's law is under the elastic limit itself. So if it is going to cross, then it is not going to be applicable. Okay. So if you simplify this one, the entire thing, okay, when you reach a plastic flow region, stress is material dependent. Okay, so let's say that is for sure. Okay, material dependent, like when if it is in the plastic region, it will definitely extend. So cross sectional area will change, right, due to the thinning effect of the metal or a material, right? And then the stress results will ultimately change. For example, when you do a tensile test after reaching a plastic region, you will start to shrink. That is for sure, that we had seen it. If you consider the ETM testing machine, so it will try to uh, add the tension force, and then at the exactly center it will try to yes, shrink. When this happens, your load matrix changes, as now you have a combination of tensile and the shear. Okay, so yeah, so in short, in the nonlinear, stress is dependent on the material, but in the linear analysis, stress is independent of the material. So again, to conclude here, same one, stress is independent of material for a given cross-sectional area and the length and applied force. Steel, aluminum and brass will give the same stress results. In short, it's clear, right, for everyone? But displacement depends on the material. So obviously stress will remain the same, but when it comes to displacement, it will be changed. Okay, this is what you need to remember. If anyone asks, in the static analysis, if you have the same cross-sectional area and if you have the different material, obviously stress will remain the same, strain will change, that is displacement will change. I hope it is clear. So how the displacement will be calculated, change in length to the original length, that is known as the strain, and obviously depending upon the material, the Young's modulus will vary, and then obviously displacement will change. I hope this is clear for everyone. I don't need to explain much. Go to the next slide. Now, important thing is the what is true stress strain and the what is engineering stress strain. Is it really matter? Does it matter? Why we use it? Okay, so before getting into the true stress strain, so we'll jump into what exactly the engineering stress strain. Okay, so let us go through this particular para. A standard tensile test produces what we typically refer as engineering nominal stress strain. Okay, if we have the tensile testing where we utilize the machine and calculate the stress and strain, right? So that is known as the engineering stress strain in short, right? So here a sample in a question is stretched using the testing machine and the displacement caused by the load are measured and recorded. That is for sure, right? So I think in the final year everyone might have done this testing where we just using the machine we just apply the load, and then depending upon the loads like increment of 50 or 20, and then we just note down the displacement. Okay, yeah. So now we know the initial shape of the specimen, right? And then we know the cross-sectional area. We'll take that into account. We can infer the level of the stress and strain at any point during the stress test. Okay, meaning we can simply convert our unitless load displacement plot into engineering stress strain plot. Okay, this is the engineering stress and the strain plots. Okay, engineering stress strain curve. Okay, so this is force versus displacement. Now, how do we calculate engineering strain? That is change in length to the original length. Okay, we have the N0. What is this? The stress, engineering stress, which is equal to force per unit area. So this is the initial area of the specimen what we have taken. So with this, in the UTM machine, we are calculating engineering stress strain, right? Now, this specimen changing shape as load is increased, meaning that the values that we used in our calculations above, namely original length and the cross-sectional area, becomes less and less valid or less true. In the sense, they might not be valid. Correct? So cross-sectional area in the ATM tensile machine, so it will try to change, right? The length will also change, correct? Now, this specimen is thinning due to the Poisson's ratio. So this is very important. Thinning happens due to Poisson's ratio that I'm going to explain in later session. Okay. Also increase in the length, meaning that the stress is actually higher than the our nominal calculation and the incremental strain is lower. Okay. In short, whatever the stress we are calculating from this, it is exactly higher, okay, than the whatever the engineering stress we have it. So now how do we check that? So this is the Poisson's ratio effect. The Poisson's effect, we can call it, thinning happens. So if you are going to just apply the force from the both the sides to tensile force, the original shape is like this, and then it will keep on changing the shape, and exactly at the center it will have the thinning effect like this, and then exactly at the center it will break. Well, so now about the true stress strain. Now, how do we calculate this? Very important. Okay. So, under the assumptions that the volume of the material remains a constant for sure, okay, throughout the test, taking the product cross section and the gauge length yields the same result regardless of what stage of the test is done at. Correct? So this is obviously only holds the true prior to necking. Before necking, so this will remain the same. And then the belts are off, and then stress at the failure must be calculated after the fact by measuring the area of the cross section at the fracture surface. Okay. So at the once it fractures there, we need to calculate the area of that particular region, and then we need to calculate the stress at that region, because we are taking the initial inert area, right? So at this region we should take this area and calculate the stress. Obviously it is higher, right? So hence, so if we just try to do that, we have the assumptions, that is volume remains the same. So area into length, which is equal to area into length, initial area, that is the final area, we can take it. So I would like to find out the intermediate area, that is A naught L naught divided by L. So this is how it is formulated. Now, oh no, 0 is the original, and I denotes the instantaneous, that is the intermediate, we can call it. Okay. Now, if we know to stress force over the instances area, the formula we know that, right? And then that is the strain is a change in length to the original length. Everyone knows these two. And then we can manipulate the equations to allow to calculate the true stress from the from only engineering stress and the engineering strain here. So now you can see, if you would like to find out the true stress, we'll consider this into account, force divided by area, I intermediate area. So we need to put this one at that particular failure, right? So if you would like to measure the stress at that region, we should consider this area. But to find out this area, we have this one, A naught L naught divided by Li. So you just reverse it and add it here, you will have this one. And then we have the engineering strain, that is change in length to the original length, here delta L, which is equal to Li minus L naught divided by L naught. And then if you formulate this, you will have this one. And then what we need to do is engineering stress is equal to F divided by A naught into bracket, we have the engineering strain plus 1. So that is, if you just move this one that side, engineering strain plus 1, which is equal to Li by L naught. So for this we have substituted this, right? And now engineering stress, which is equal to F by A naught, is the engineering stress into engineering strain plus 1. If we do it, we'll have the true stress, right? And then how do we calculate the strain? So this is the integral form of delta L by L. So ln of L naught by L. So now L naught by L. So we have, so just the value, we have it here. Just move it this side. So ln of engineering strain plus 1, which is equal to true strain. So this is how we calculate the true stress and the true strain at that particular region. Okay. In short, whatever we are doing in the static analysis, it's all related to like engineering stress, engineering strain itself, because there we take the constant thickness, but if it is deforming, if it is under the nonlinear condition, then we consider the true stress strain. There we have the nonlinear analysis, the failure with respect to failure theories. We have the different algorithms to run the analysis and give you the results. Yeah, but under whatever the static analysis we are doing, it is under the consideration of the elastic region, so it should be fine. So now again, so what is the difference between true stress strain at that elastic region? So that we need to cross verify, right, before concluding, because people say we should only take the true stress strain into account. Why not the engineering stress strain? Let's see that one in the next slide. You could see. So that is what, whether does it matter? So as mentioned previously, there is not much disparity between engineering and true stress strain values at lower strain. So that is what I told. However, load increases and the specimen begins to change the shape more drastically. The difference does become the relevant, and hence we would always recommend utilizing true stress strain data in your FE model. Correct. So let's just look at the same thing here. If we have engineering stress as 100, okay, strain is 0.01. So you can see this true stress value is 101 and the engineering strain value is 0.00995. So the percentage difference is only 5%, not much. And then if the engineering strain is 0, then there is no difference at all. So now here 150, 0.5, so here 157, the stress slightly increased, right? And then here it is the difference, here 2.42. Likewise, if you keep on increasing the stress value, if the strain becomes more, the difference is much. And here you could see when you have the stress, 18.2% strain is whopping to 22.5%. Okay, 22 point difference between in the stresses at the 18.2 strain. Exactly. So this you need to remember. So if you keep on increasing the strain value, so this does matter. So I hope it is clear for everyone. So yeah. Now the Young's modulus, very important term, what exactly this is. Okay, so we call it as the modulus of elasticity. That is a mechanical property which measure the tensile stiffness of a material. So stiffness of the material will be measured with respect to Young's modulus. Okay, so this is the slope, we call it as from here to here we have the yield strength value, right? So this is the stress strain curve, in that this is the value. So 300 megapascal if you consider. So yeah, Young's modulus is denoted by letter E, that everyone knows. For the beginners it is very important. So it is measured in form of the megapascal or the gigapascal. So mostly it is in gigapascal. Okay, 1 pascal, which is equal to 1 Newton meter square. Remember that. Now very important, let's say in a linear static analysis applied to a majority of FEM models follows the principle of Hooke's law of the elasticity. That is, a stiffness of the part follows the elastic portion. This is the one in the stress strain curve. In the linear static analysis, very important. Okay, up to here only we do the linear analysis. Once it crosses the yield point, it's all in the implicit and the explicit analysis. Well, now majority of the FEA analysis linear analytic, which, okay, the same statement here, and then we'll need the additional stress strain curve in the non-linear analysis. Okay, the non-linear analysis, we take the stress strain curve. This is the curve, so depending upon that we finalize the results. Yeah, and then in the figure we can easily calculate the Young's modulus. So in this case I can see, so first the yield stress is the 300 megapascal. If you have it, the strain is this much. So what is the Young's modulus? Young's modulus, which is equal to stress by strain. So you put it here, 15 was a 15 twos are, so it should move twice, and then this becomes 200 gigapascal. Okay, mega to giga it has converted, so it should be yeah, for yeah, correct. Yeah, so this is 200 gigapascal. So this is how we calculate. So very important. So this is how the relation between the Young's modulus and the stress and strain. So Hooke's law state the same. Okay, so for that only, to count the two stress strain, we have the stress strain curves into account. From there we can exactly calculate what exactly the strain, what exactly the stress for the given component. So we don't consider the engineering stress strain into account in any analysis, in short. Okay, if someone asks you, you should remember what is the main difference between the engineering stress strain and the two stress strain. Yep, the next one is the Poisson's ratio, one of the major impact, the FEA. So what is this? So this is the Poisson's effect we call. So let's say initial design is the blue, purple, you could see this is the design change. We have the delta L naught here, delta L is here. This is the change which is happening. We divide these to get the Poisson's ratio, that is lateral strain to the axial, that is transverse lateral strain to the longitudinal strain we call it. So the ratio of the transverse strain to the axial strain. Okay, so once you do that, you will get the Poisson's ratio value. So this is different for the different material. Most of the material will have the range from 0 to 0.5. Okay, now but if we have the material like the rubber and all elastomers, it is comparatively more. You could see this is the table. Oh, for the rubber it is exactly 0.5 we can say. Okay, it will have the same deformation. So I hope you had seen, you can imagine rubber, just if you drag it, you'll understand how it is forming. And for the gold it is 0.42, almost near to this. For the copper it is 0.33, aluminum alloy is 0.32. This is the Poisson's ratio. When it comes to stainless steel it is 0.3, so we had seen it, right? We know that. Steel also it is 0.3, cast iron is 0.21 or 0.26, depends. Okay, concrete is 0.1. Cork directory fails, right? The cork ball 0. Metallic glasses 0.26 to 0.49, so depends. Metallic glasses, okay, sometimes they bend, right? And then glass is the 0.18. Yeah, so the sand important is the 0.2. Yeah, well, so these are the Poisson's ratios you need to remember. Okay, well, so this is all about the Poisson's ratio. So that is the ratio of the transverse strain to the longitudinal strain, and then they will take into account, then you will get the ratio that is known as the Poisson's ratio. Yep, next is the assumptions when it comes to geometry. These are the assumptions. Let's say if you imagine this geometry, okay, so here the displacement values will be small so that it's a linear solution, so there won't be much displacement, so it is under the elastic limit. Okay, so if it is more than elastic limit, let's say we have the Young's modulus 300 megapascal. If you see the results more than 300 megapascal, so you need to consider that that is failing in the sense whatever the results you are expecting above than that, they are not exactly we are looking for, so we should consider it is failing or it is going above the elastic limit. Okay, it is not safe, or the factor of safety is not good. Okay, just remember displacement are small, and then the stress behavior outside the area of interest is not important. Therefore geometric simplification in these areas do not affect the outcome. Let's say so here if I just remove this particular fillet and the outside fillets and all, and here also if I remove and if I sharpen this, so here if you would like to calculate the results, so it is mostly impacting on this region and the bottom here. right? So there are the important stress regions, and there we need to calculate. So if we suppress these regions, that is not going to affect a lot for our model. So that is what they are going to tell here. Model simplification is very important. So for meshing these things and all, it requires a lot of time. So if you just make it sharp, then you don't need to invest more time for the meshing and all. Okay. So depending upon the area of interest, so we need to deal with the model. Okay. So only internal fillets in the area of interest will be included. So at this region it is very important, or else we'll have the stress hotspots. So which will lead us to have the more stress, because the area will become zero, that is infinity, and then your stress will drastically increase at that region. So we need a certain area to distribute the force. Yeah. So local behavior at the corners, joints, and the intersection of the geometry is of the primary interest. Therefore, no special modeling here. Very important. So joints and the corners, we need to have the fillets to capture that. That is what they're telling. So we have the decorations. So if you have the name and all, so that is not going to impact a lot. Okay, we can exclude them. We can just remove them. So yeah, that is what the assumptions related to the geometry. I hope it is clear. Next one is the material properties. So some of the assumptions related to material, we have it here. Material properties will remain in the linear region, and non-linear behavior of the material property cannot be accepted. Okay, so whatever the properties we are going to take until Young's modulus, that is the elastic limit, we're going to consider the properties into account. That is Young's modulus on the Poisson's ratio. The strain, right? The material properties are not affected by the load rate. Okay, so it is not going to change with respect to load what we are going to change. So it is under the elastic limit. So the force is removed, the model will come back to the original shape. The component is free from the surface imperfections that can produce stress concentrations. Okay, so if you have the surface imperfections, so that we should not consider. Okay, all the simulations will assume room temperature unless otherwise specified. So yeah, most of the analysis, 99.9% analysis under the room temperature. We don't define any temperature for this. The effect of relative humidity, water absorption on the material used will be neglected. So that and all we won't consider at all in the simulation. Okay, in short. So we just consider the normal room temperature and just start working on the static analysis. Okay. No compensation will be made to account for the effect of chemicals corrosive wear. Yeah, this is for sure. So we consider the model which is fresh. It doesn't have any defects, or it doesn't have any corrosive wear and tear on the model. Okay, that if you have it, we won't even consider that. That's clear, I think. If you have the model with the corrosive things and wear and tear, and if you can simulate it, and it will fail, but if you do it in the analysis, it won't get the same results. That is what the conveys. So we don't consider these things into account. Well, so we have some assumptions related to boundary conditions. So you could see we have the nuts and bolts here. So this is the boundary where we have considered to connect these two components. So let's see what and all there. The displacements will be small so that the magnitude, orientation, and the distribution of the load remain constant throughout the process of the deformation. So this is what they are telling. So it shouldn't displace more. Frictional loss in the system is considered to be neglected. So whatever the friction is happening, so that we won't consider at all. So with respect to friction, we have some stress induced, so we won't consider that. We neglect it. All the interferencing component will be assumed rigid. So wherever there interference, we have the interference if it has it, so it is completely rigid. So we don't consider them as a, like if it is impacting or if it is pushing inside, so it's a complete rigid we consider. The portion of the structure being studied is assumed as a separate part from the rest of the system, so that any reaction or input from the adjacent feature is neglected. Okay. So whatever the component you are considering, these two are the separate adjacent parts. Okay. Well, so these are the few boundary conditions. Assumptions related to boundary conditions, material, and the geometry. We had seen it, and the fasteners we have it here. So when it comes to fasteners, the residual stress due to the fabrication, preloading, that is pretension, the welding, manufacturing, will be neglected. We don't even consider these all things. All weld between the component will be considered as ideal and continuous. So whatever we have the weld and all, so that we considered as ideal or the continuous. Okay, the welding. it comes under the part itself we consider. Okay, the failure of a fastener will not be considered in the model. Like when you do the analysis, if this particular fastener is failing, we don't consider this particular fastener effect, the failure of the fasteners. Okay, so that is not our area of interest when it comes to the analysis. Yep, so these are the few assumptions. I hope it is clear for you guys. And now when it comes to analysis, FEA, FEM, whatever we do, so we don't get the 100% accurate results. That everyone needs to understand. So it's all assumption. Okay, we get the approximate results itself. No one in this dash is going to achieve the 100% results. That is what you should remember. There will be slight difference. Let's say this is the problem we consider. Okay, integration of x squared plus 6 of dx. If we consider this is the area, so if you just consider this curve, we have the formula x squared plus 6. Okay, and then if you just do the integration, okay, this will become 1 by 3 x cube plus 6x minus 1 to 1. So if you solve this, you're going to get 38 by 3, 12.667. Okay, now if you want to solve this one, the area of this particular model in FEM, that is in the analysis, we need to mesh this area, right? So we'll be having different types of elements depending upon that we measured. So let's say we consider the quads now. Okay, we have the one quad element, that is we call is tetra element 2D. Okay, it has 4 nodes, and if you just do this one, this is very coarse mesh we can consider. So if you do that, so we have the percentage error of 5%. And now let's say we would like to mesh this one with a finer mesh. So likewise you could see, so until here we meshed it, but we have added extra the area here, which will approximately compensate these two, but we have the difference of 1% approx. Okay, then so I'd like to mesh it still finer. You could see we have just meshed it like this, and then here we have the difference of 0.3%. Now if you just mesh it again finer, we'll have this model. Here you have the 0.08% difference. So in whatever the analysis you're going to do, so we're gonna mesh the model to segregate them into a small elements, and then we extract results on that small elements. So the results will have the approximate solution or the accurate solution. Okay, that approximate solution, so what is the percentage error we are getting, that depends solely upon your analysis, what kind of mesh you are considering into account. I hope this is clear cut for each and everyone. Yeah, well, I think that's all from this session. I hope we have gone through most of the things. We had seen how the stress will behave for the different materials. Yeah, we had seen it, then day 2 stress strain, engineering stress straining, Modulus, Poisson's ratio, assumptions related to geometry, material boundary, as well as the fasteners. And we had finally seen how our FEA results will be correlated with the exact analysis or the exact values. Okay, I hope this session might find you guys useful. Well, that's all. We'll see you in the next session. We heartily thank you all for watching this video. If you enjoyed this video, don't forget to hit the subscribe button and give it a thumbs up. Follow us on Facebook, LinkedIn, and Instagram for behind the scenes content and the updates. Stay curious, stay awesome, and see you again in the next video.